And what we want to do here is that we want a single number to summarize this situation and tell us if the points are more or less in a line. All right. Now that sounds a little bit abstract, at least for now. Why would we do that, and what information can we infer from such a descriptive? So first thing first is we would like a descriptive to tell us if the points lie somewhat, all right, somehow in a line, all right, in a line. And of course, a line can be roughly, all right, roughly said to be uh, either having this quadrant to this quadrant, all right, or this quadrant to this quadrant. Yeah. So if the points are such that they are mostly here and here, then it's a line. It's a line with kind of a negative gradient. If the most of the points are in the first and the third quadrant, then it will be some sort of a line, right? You can have spurious points, outliers, sprinkling in second and fourth quadrant. But if most of the points are in the first and third quadrant, then you can say, yeah, there's some sort of a line, yeah, with a positive gradient. Yeah, so that is the motivation that we seek. And then the remaining question is questions will be, so what, right? If we have such a descriptive, and how do we define this descriptive? Let's answer the first question first, which is kind of easier. How do we use this descriptive? Kind of ignoring how we define it first, how we can find out such a descriptive, how we can calculate such a descriptive first. So how can we use it? What does it? Why is it meaningful to us? Now, if you are trying to program a robot to see if these data points, remember these data points can be people in a video, yeah, so if are people lining up in a line, something like that, is the robot detecting some sort of a linear feature, a line? Is it seeing a line, basically? Yeah, so that is a very difficult thing for robot to do. So we'll like to have a sort of an LED light, an indicator to say that, it will light up thing if there is a line, and otherwise darkens if there isn't a line in the picture. So that would be very useful if we can define such a descriptive: light up and don't light up, or very strongly lit up and kind of dimly lit up if it's kind of like a line but not really a line. So it will be a very nice sort of a indicator, the strength of being linear. We can start with that first. Yeah, so the strength of being linear, how linear is the robot seeing? So that's one. But of course, this descriptive was developed at a time when robot wasn't the biggest fanciful idea in the minds, but more on the basis of having a more objective way to describe the spread of the data, the sprinkling of the data when you are performing two measurements. So for example, when we talk about obesity, right, height and weight of people, one scientist might measure a bunch of samples around his or her locality or country, and another scientist may measure a bunch of samples, and even if it is very unbiased and randomly selected, it will be based on his or her locality, right? Very different. So is there a sort of a very objective, data-oriented way rather than subjective human assessment way, right? Is there an objective way to describe the linearity, right? The claim that the heavier, or rather the other way around, the taller the people, the heavier they weigh, or the lack of it. No, it's not true. The taller doesn't mean you're heavier. Okay, so you need data to prove that, right? Or disprove that. So is there a objective way to say, yeah, it's a line? That means it's quite proportionately sort of scientifically or data oriented way to show that, yeah, the taller the heavier, or it is not really linear, thus disproving it, disproving the claim that the taller the person, the heavier he or she will be. So that is more on a more objective seeking kind of motivation that we also require a descriptive. Yeah, so we can see that with the development of AI and all this, it is increasingly useful for covariance to come in to help calculate, right, and inform the robot that yes, there's a line, or there's a very strong line, or it's somewhat of a weak line, and then you do the right thing for a weak line. So it's really useful descriptive in that sense. Then the second question is, how do we define it, right? So the idea is this, is an interesting one. It starts with, if we look at this particular point, it starts with asking us to calculate this particular point. Okay, I happen to be calling this point 1, let me see, point 2, and point 3, point 4, and point 5. Yeah. So if we look at this point 3 here, then we are asking to calculate this distance versus this distance. And no doubt this distance is x3, because this point will be x3, comma y3, right? Whatever the data that has been measured. So it will be x3 minus x bar. And this height here will be y3 minus y bar. Agree? Of course, y3 is the coordinate. It's sort of a starting from the 0 axis. But once you have y3 minusing y bar, you are calculating the height of this point, not as y3, but relative to y bar. So that means y bar is 0 level, and y3, however high it is or low it is, will be plus or minus accordingly. Yeah. So we're going to find this and calculate the area. So we're going to multiply them together, and thereby essentially doing this. Yeah, so xi minus x bar times yi minus y bar. So that is one such rectangle. Okay, and this is a positive area. Yeah, so it's a positive area because clearly x3 is larger than x bar here, y3 is greater than y bar. So the area will be positive. But if we look at a point like 1 here, where the x length will be x1 minus x bar, and quite obviously from the diagram here, we find that x1 will be less than x bar, isn't it? And so this length will be minus. And before we think that it will be a negative area, this height here is y1 minus y bar, and because y1 is below y bar, so it's below sea level, and it's also negative. So therefore this area will also be positive because we multiply two negative numbers together. So in other words, points that are in this quadrants 1 and 3 will have positive areas, okay, when they are multiplied together. So they will have positive areas, which is kind of nice because it's trying to say that it will have positive gradient as well. Yeah, but let's not jump to that conclusion yet. And quite also clearly, a point such as 4, or if you have a point in the second quadrant, we will find that the resulting area product will be negative because one of the x or y will be negative and the other one positive. So let's look at point number 4 here. Point number 4, x4 is greater than x bar. So this horizontal length is positive, but the height is y4. y4 is below sea level of y bar. So this height here is negative, and therefore the area is negative. So you will have a bunch of plus areas and negative areas. In my example here, most of the areas are positive, right? Yeah, you can see that the area, not just the length of the height, but the area that is being induced by the point, most of them are positive. And then if you subtract a big chunk of negative, we'll let the numbers play themselves out, and then eventually we have a number, a net number, right, which is the sum of all these areas. And the way we say it is basically uh, summing it all together from 1 to n, the number of points. So in my case here, I have 5 points. And to kind of not blow it up, but to find the average square, right? The average square. So when we add up plus areas and minus areas, we find the net. Yeah, this summation will also add in negative areas. So it can be that covariance eventually end up being zero. All the areas cancel out exactly, and that's possible. And that's very interesting too, right? Certain occasions will have that. So when the areas, most of them positive, minus some of the negatives, resulting in a net positive, we want to kind of get a sense of average area per point. Yeah. So we're going to define it as 1 over n. Supposed to be n, but if you recall the sample variance, it was over n minus 1. And so we like not just to make it symmetrical with sample covariance, but it will be necessary for us to also follow this minus 1 convention. And when we do that, this is our sample covariance of x and y.